Hello, everyone. My name is Junhe Zhu. I'm currently a postdoc at MIT. I'm now working with Professor Thomas in the Department of Mechanical Engineering and working with Professor Martin Bazant in the Department of Chemical Engineering. Today, my topic is characterization of the large deformation plasticity of pure lithium. Thank you for watching my video presentation. And if you have any questions, please feel free to let me know. And you can join my Zoom, personal Zoom meeting room via this link, or you can also send me emails. My email address is provided here. The background of my research is the scaling up of e-transportation. Of course, this scaling up is supported by today's lithium-ion technology. And today's technology, the maximum energy density actually achieved, reported, is about 250 to 300 watt-hour per kilogram. This is at the cell level. And with this, such a energy density, what can we do? Of course, we can build electric vehicles. So today's electric vehicle have a very long mile range, about 400 is the state of the art. This is a Tesla Model S Range Plus. Can we use these batteries to build an electric airplane? The answer is probably not. Here, this is a NASA Maxwell X-57. This is only an experimental aircraft. So the range is very small. It's about less than 100 miles. And it just took flight last year. Of course, there is a very long way to go from this experimental one to commercial ones, large aircraft. So what can we do? We have to develop next generation batteries. By next generation batteries, what we usually mean is lithium metal batteries or all-solid state batteries. Actually, in all-solid state batteries, many people also use lithium metal as their anode. So lithium metal becomes a very important material for us to study. So this study is focused on its mechanical behavior. There are so many lithium metal studies, so I want to put them together and let you see the length scales of all studies. Of course, when we get a lithium metal, it is a foil, and we can use this foil to build different batteries. The thickness of a foil is usually less than 1 millimeter. And this foil is, of course, a polycrystal. So one grain is about 100 microns. And in some cases, lithium dendrite grows. Its initiation is about 1 micron. After fully developed, it can be like 200 microns. And as many of us know, on the anode side, on the surface, there is always a thin layer of a so-called SEI film. So this SEI film is about 5 to 100 nanos. Also, in many publications, many people study different phases of lithium. For example, this is a whisker. So a whisker is usually about 0.5 to 5 microns. And many people also study the surface roughness of lithium foil. It's about 0.5 to 5 microns. And also, many people use focused ion beam to cut a pillar of lithium. And such a pillar usually have 1 to 10 microns in diameter and also in height. So this picture gives you roughly an idea how many length scales there are. Why is this so important? Because according to our existing knowledge, there is a very strong side effect in lithium metal, particularly in mechanical behaviors. For example, this plot is made by Professor Matt Farr in his recent publication. So we can clearly see that there are a lot of studies as well already, right? The x-axis is length scale and y-axis is yield stress. So there are many publications tested the bulk strengths, and also there are a lot of publications focused on the length at a nano and micro scale. And more recently, there is a paper from Professor Ting Zhu's team from Georgia Tech. So they developed a testing device based on AFM, and they tested one whisker. So as I mentioned, one whisker is less than 1 micron, around 1 micron. So we now have more data in this range. Different color means different orientations because it's single crystal. So clearly, there is still one gap between micro and macro, right? Nano and macro. So this is a mesoscale gap. And our group is currently working on this gap. So why is this gap so important? Because it covers a lot of things in lithium study, from roughness, grain size, to lithium foil, the thickness, all the way to the diameter of a coin cell, right? So that means if we want to build a battery, this range is really important that everyone have to deal with. And the second question is why it's not oftentimes investigated, because there are 3 difficulties, mainly because pure lithium is highly reactive and flammable. The first difficulty is the sample preparation. So currently, many people just use razor blade or die cutting, but these 2 technologies cannot produce very complex geometry. And of course, we can use some advanced technologies like EDM, but cooling is a very difficult problem, and cleaning is very difficult. And the testing have to be performed in a gas-protected environment. For example, glass box with argon. This is a very common choice. And this last difficulty that today I will point out is the large deformation of pure lithium. According to our test result, you will see that lithium is really a perfect ductile material. So it will be very difficult for testing and for modeling. Starting from the first challenge, we developed a very safe laser cutting of pure lithium foil. Here, we cut the lithium disc in a glass box, and then we designed a small chamber, and it can be assembled in glass box, and we stored lithium foil in this chamber. Later, we take this to laser cutter. This device is designed to be transparent to laser, so laser can cut the sample when the sample is still in the chamber. These are the samples that after we cutting, and after disassembly, we can get the samples. So of course, there will be a heat effective zone, right? So this is the edge. We can see the edge is really in a very high quality, and the heat effective zone, as we observed, it's like less than 1 grain size. So we think that the heat effective zone is really small. And we also perform tests to validate that. We see that samples with laser cutting or with die cutting, we observe the similar test results. So we can safely say this cutting technology is very reliable. With this cutting technology, we designed 5 different types of mechanical test samples. So this is uniaxial tension, central hole tension, notch tension with a very smooth notch, and sharp notch tension. And this is probably the most complicated one. This is a simple shear test. As you can see, this sample have a very, very complex geometry. So that's the advantage of laser cutting. Okay, and we for the second challenge, we actually start from understanding it. So we performed a test, performed a controlling test. We did test immediately after cutting, and 10 minutes, 60 minutes after cutting, and on different days. So this is what we observed. X-axis is displacement, y-axis is force. So we did observe difference in stress strain curves or force displacement curves. So there is a strong effect of air exposure. However, we find that if the time is very short, like 1 minute, the difference is really small and it is really acceptable. So we also took the samples to see on the SEM to see their microstructural evolution. So immediately after cutting, everything is very, very clean and grain boundary is very clear. So 10 minutes, oxidation and humidity plays a very important role. On different days, after 60 minutes, you will see a very, very rough surface quality for the sample. So this is the power of the exposure to air. So in our test, we avoid this by putting it in argon atmosphere, and we also develop some small devices to finish the test. And above all, we do all the tests within a very short test duration. Okay, and for third difficulty, actually, today is my focus of our test results. See here, this is the nominal stress strain curve, or the engineering stress strain curve of uniaxial tension. We can see that this is really interesting. There is a clear peak force or peak engineering stress. So that means there is necking. So before necking, this range is really short. It's about 0.05. Between 0.05 to all the way to 0.65, this is a long, very long stage of diffuse necking. And after that, there is localized necking. So lithium metal is really interesting in terms of mechanical behavior. And to roughly give you an idea, I here put 5 different other materials for you to compare. So there are brass, there are steels, and different steel aluminum, and none of them behaves like pure lithium. Of course, there is one material, it's a zinc titanium alloy. It's really soft. It's like our lithium. However, lithium is the only one with such a short pre-necking stage and such a long diffuse necking stage. So that means the material start to flow. And after that, we take the sample to see the SEM, and we find that here, this is the fracture plane. So lithium foil really fractures in a perfectly ductile fracture manner. So that means localization happens, and the material is super soft and ductile. Okay. These are the test results of the other 3 types of multi-axial tensile tests. They are uniaxial central hole tension, sharp notch tension, and smooth notch tension. So for each of the tests, we performed 3 times of test, and the repeatability is quite good. Only difference is here, notch tension, smooth one. There are some different behaviors in different curves, but this is still acceptable. And we also did this simple shear test with, of course, simple shear. The test sample is really small, and there are only 6 to 8 grains in the cross section, in the smallest cross section. So we observed more uncertainty in the force displacement curve. And we also did the DIC measure of the strain, and we processed the strains according to the DIC result. And we found that what is really interesting is compared to those tensile tests, shear tests, there is, as expected, there is no necking. Material really just hardens, right? That's because there is no reduction in the gauge length or the gauge area. There is no way to neck, right? Okay, and our experimental results get more validation from the microstructure observations, and the observations are really interesting to us. For example, we observe that a lot of slip lines are on the surface of the sample, and in each grain there are different slip lines in different orientations. That means there are at least 2 active slip systems, and as a result, there will be a lot of waves on the surface. So a wavy surface is observed in almost all the tensile tests. On the other side, as I said, it's a perfectly ductile fracture material. So here, my laser point is going here. So this is one line. That means originally there is a plane of cross-section. After fracture, it becomes only one line. So that by this, we mean that lithium is really perfectly ductile, right? Okay. besides the experimental data today I showed, actually we also did a very careful theoretical and numerical modeling of pure lithium. And we find that the material is not only rate dependent, it's also anisotropic. But in the in-plane direction, it is isotropic. So we developed a rate-dependent transversely isotropic plasticity model. So these are today, actually time is very limited, so I only show you the result. Our model can do almost perfectly to predict the trend of the and the magnitude of each curve of the four complex tests. Okay, if you are interested in our modeling, please follow our upcoming paper for more details. Okay,